So stages, you could almost think of them as, if you draw an analogy to traditional query plans, it's almost like a dam, right? A stage is a dam after which you can resynchronize or rethink things. So like the work that we did with progressive optimization, but in general it's a dam, it's a synchronization point. So stages really ensure three properties. So one of them is that the virtual machines for the next stage will be available, right? So that's what has to be ensured when we work on a stage. We're starting to allocate the virtual machines that are needed for the next stage, right? And that will be done by monitoring and also determining how many machines we will need based on some data distribution, well, partitioning and whatnot. All workers then are set up and ready, and the data of the previous stages is stored in a persistent manner for fault tolerance purposes. Right? That's really like similar to what Hadoop would do in its distributed file system. However, stages are not necessarily single operations, right? The packed compiler can choose how many operations to group into a stage. In this way, we can also exploit pipelines and get pipeline parallelism. So we have different kinds of communication channels for that reason. We have network channels, which must be in the same stage, right? So it's a pipeline. Pipelines things to another machine. Then we have in-memory channels, where the vertices obviously have to be on the same virtual machine, and the vertices must be in the same stage. And then we have file channels, where they have to be in the same machine, but they can be in different stages. And it's really the task of the packed compiler and the continuous optimizer to decide the channels, right? So how to do the wiring. So we've done some first evaluation of that system that basically so far demonstrates the benefits of this dynamic resource allocation, where we just used basically some variant of the grade sort benchmark, which is sorting and aggregating 100 gigabytes of integer numbers, and basically we aggregate the top 20% and want to get an exact result. And we compared that to Hadoop. So we did the first execution as MapReduce jobs with Hadoop, where we basically have 3 MapReduce jobs on the 6 virtual machines. Each of them is 8 CPU cores and 24 gigabytes of RAM. And I should again say, actually, that was machines that we bought through a shared university research grant from IBM. So thank you, IBM, for that. And we used the TerraSort code for sorting and some custom code for aggregation. And the second execution was as MapReduce jobs with Nephilet. So we actually have a compatibility layer that we built for the Nephilet packed compiler, right? So that we can actually run Hadoop MapReduce jobs, where Nephilet then controls the resource allocation. So we get this more flexible resource allocation scheme and elasticity from Nephilet, but we can actually execute Hadoop MapReduce programs. So the idea there is that we adapt allocated resources to the required processing power for each stage or step. And when you compare that, the interesting question here is now the CPU utilization in this case. And what we see here on the left, we see how that works for Hadoop. So we have the initial phase where we have 3 machines busy on the map job. So what you see here basically is the job, this resource CPU utilization over time, distributed for weight, system, and user. And we also see here the network traffic. And we see basically that we see those 3, so we see a utilization of close to 80% or so, which is pretty good here at this stage. And then when the mapping is done, so the reducing is already starting, then there's some weight, a lot of network traffic, and the reduce phase is going on. In the reduce phase, we really don't get a good utilization because that's not happening on that one node. So that means we are getting down to a utilization of something like 30%, so 3 machines are idling. Whereas with Nephilet, what we see here is that actually we're getting also a good utilization because we were able to deallocate those machines, right? And those are now available for other tasks and other computations. So this elasticity that you want to have on the cloud is available. So this was just the very first evaluation that we have done with this Nephilet system that we have built. So we have this pool resource utilization here, and then because of the automatic deallocation, we see the improvement. So with that, I want now to move into the third part. So I've given you an overview now on the one hand of this programming model that we're using, an overview of actually the execution platform. Now the question is, how do we tie those together? How do we actually translate those packed programs into those parallel schedules on the Nephilet engine? And parallelizing the execution, if we look at that, it's basically similar to query compilation, but then we have the adaptive component that we're currently still working on very much. But you will see a lot of similarities to traditional database optimization in the first stage, with one difference, and that is we have big problems of putting the cost model here. But in general, what we have is, the goal is we have a pack program that needs to compile down to net-valid DAGs, where we have to set the communication channels, are those network channels, memory channels, also decide the degree of parallelism based on the output contracts for an initial version. And then we have to span that across the nodes. That's really what the network will do in order to do the parallel execution. So that's then the graphs which are then parallelized and executed in parallel. But overall, if you look at the code consists of a shell of those 3 layers. There's a user function, that's really the code that the user provides for each contract. So the example that we see here is actually the initial example of this TPC-H query that I had shown you earlier in the talk. So we have 2 user functions for map contracts. We have another user function for a match contract, another user function for a reduce contract. There's an example how the match, for instance, would look like in this case. And then we have this packed code, which is actually a code that the compiler has to generate, which is then really doing the grouping. And on top of that, then the net-valid code has to, the logic has to be added for this communication channels. So that's how the compiler, on a high level, will translate those programs.
So the source.
Yeah, I'll go back. Sorry.
The source is for example, the top left, that box. That's
actually, the source is a couple of those, right? The source will be you have to provide one function for each UF field. So this here is a definition of UF3. You will also have to provide UF2, UF1, UF4.
And that's viewed as easier than SQL.
That's actually, yes, that's the interesting thing. So people
by what, like, bytes, or I'm trying to understand by what metric this.
So I think people are very familiar with the Java programming world, and I think the big problem here, at least that's the feeling I get from this when I attend those user group meetings, is the impedance mismatch.